Welcome everyone, this is Ronald DiMera at the University of Central Florida with my colleagues Dr. Jun Wang, Zunchao Chen, Naveed Koshavi, Dan Huang, Dr. Wuji Wen of FIU, Dr. Yiran Chen of Duke University. I'll review our paper. It's appearing in the May 2017 issue of Transactions on Computers, Energy-Aware Adaptive Restore Schemes for MLC STT-RAM Cache. The paper leverages memory referencing behavior to reduce energy expenditures while also addressing vulnerabilities of read disturbance and write disturbance. So as an overview, why consider multi-level cell MLC spin transfer torque on chip cache? Well, cache leakage and overall energy consumption are significant concerns for multi-core dies, so energy and area-sparing alternatives are sought. STT is composed of MTJs, which are non-volatile devices. They have near zero leakage, high cell density compared to SRAM, and the density can be increased using a multi-level cell design. What is the structure and mapping strategy? Well, using the figure numbers shown in the paper, we have here a serial MLC with a soft bit and hard bit. Smaller area MTJ is the so-called soft bit, and the larger MTJ is the hard bit. The idea is the write energy cost to update the cell may involve multiple write operations, and the corresponding critical current has to be watched to avoid either read disturbance or write disturbance. So taking this physical design and mapping it to the logical data structure, there's a so-called cell split mapping strategy, which is a conventional mapping strategy. And the small MTJ and large MTJs are partitioned as shown. So we're talking about the virtual to physical bit cell mapping, and we'd like to leverage the capability of the underlying device. Next, let's consider write disturbance in MLC. During a write operation, the switching current I sub W is proportional to the MTJ area A. Thus, the write current for the soft bit will not disturb the hard bit, as shown in the left half figure. However, the magnitude of the write current necessary to update the hard bit may inadvertently flip the soft bit. This vulnerability to the soft bit when a hard bit write occurs is commonly referred to as a write disturbance in MLC. The conventional approach to address the write disturbance issue is called the immediate restore scheme. It refreshes the data in the soft bit line after every write operation to the hard bit line. For example, in figure 6, we consider two arbitrary blocks alpha and beta, which are stored in the hard bit line and soft bit line respectively. In order to write an alpha data block to the hard bit line, then the data block beta of the corresponding soft bit line has to be backed up first. Then the alpha block is written, which will overwrite the beta block due to the critical write currents. Thus, as a last step, block beta has to be restored to maintain the data integrity. So those red overhead terms in the last equation lead us to the adaptive restore scheme proposed in the paper. Our thesis in the paper is conventional immediate restore scheme for write disturbance can be unnecessary, especially when it consumes extra energy. For example, if the disturbed soft bit line block beta is invalid, or if the block has a replica in a higher level of cache, or the block will be replaced soon, then there's no functional need to update the disturbed block. In light of this, we propose the adaptive restore scheme for write disturbance. The full flow chart's detailed in the paper, but the main idea of our scheme is highlighted in the red box. Here we restore the disturbed soft bit line only when it will be read soon. The remainder of the flow chart realizes a lightweight scheme to selectively restore the soft bit line. This is done only when necessary. In the paper, we identify those conditions. On the other hand, if it will not be read, we can leave that block unchanged to avoid the corresponding restoration energy demand. To deal with the read disturbance in MLC, let's take a look at the underlying read sensing strategy. As shown in figure 3A, first a sensing current is applied to determine the resistive state. The potential is compared against reference voltages to determine the binary value of the soft bit and then hard bit respectively. However, as shown in figure 9, in contrast to the switching current, the sensing current does not continue to scale down with the feature size, as indicated by the red line. Therefore, as shown in figure 2A, a read operation may inadvertently flip the value of the soft bit. This is referred to as read disturbance vulnerability. Thus, under a conventional approach, an immediate restore scheme for read disturbance can be invoked, as shown in figure 6. To read the data block beta, both the block alpha of the hard bit line and beta in the soft bit line would be read out. Since this read operation may disturb beta, the block needs to be restored in the end. So that brings us to the proposed adaptive restore scheme for read disturbance. To skip some of the unnecessary restore operations to save energy, we merge the restore operation of the disturb block with the dirty block write back operations. So shown in figure 11a, the soft bit block is fetched to L1 without being immediately corrected, and its disturbed copy in L2 is invalidated as shown in the red box. The modification of the status block is tracked by a flag bit. As shown in figure 11b, red box, only when the block is modified or more likely to be read at the L2 level, then this block will be restored. Following this adaptive strategy, then a significant amount of restore energy can be saved. To predict the read-reuse behavior of a cache block, we introduce the concept of read-reuse distance. Read-reuse distance is computed as a timing distance between two consecutive read accesses to the same cache block. As shown in figure 12 of the paper, we depict RRD and also the estimated distance to read, or EDR. Accurate prediction is enabled by the fact that cache access behavior can be grouped based on instructions PC at which they ensued, as illustrated in the rightmost table for this example. We have various code blocks which have corresponding RRDs, each of which have different PC values that directly correspond to the point of execution. There are two components within our predictor design, a read sampler and a read prediction table. The read sampler calculates the RRD of each instruction that causes a cache read. Meanwhile, the read prediction table provides a reliable RRD for a given instruction with the help of a confidence counter mechanism. In our experiment section, we use NVSIM in conjunction with Cacti to simulate circuit level area, latency, and energy of 3 on-chip cache candidates. We also use Mars x86 and DRAM Sim 2 to mimic a 2-level cache hierarchy. As listed in the table, we evaluate a quad-core processor. Results show our adaptive restore scheme promotes MLC as preferred L2 candidate, which decreases energy consumption by 17.9% and increases IPC by 9.4%. We go further in the paper to leverage the potential of cross-layer approaches to employ specific switching and computation characteristics of emerging memory technologies by providing some lightweight architectural support to adapt to the application behavior. Thank you for watching this overview, and we hope you find the approaches in the paper to be interesting.